I think we can start. Today's speaker is Professor Andrii Pilipenko with the talk on homogenization of multivariate diffusion with semipermeable interfaces. Please, Andrii. Andrii,
Please unmute yourself.
Thanks. I'm very happy to present a talk in our seminar, and this talk is based on our joint work with Olga Aryasova and Ilya Pavlikevich. It is a continuation of our previous result on homogenization. And today we consider the following model. Assume that we have a diffusion in a media with semipermeable membranes. These membranes are located on half spaces. So this coordinate is x, this coordinate is y. These are local times. So between these interfaces, we have usual diffusion with nice coefficients sigma and b. And when the stochastic process hits a membrane, there is some singularity. Informally, when you hit a membrane indexed by a number ak, then with probability p that is equal to 1 plus delta beta over 2, you go to the right, and with probability 1 minus delta over beta divided by 2, you go into the left. But this is informal explanation. These local times are considered, we consider symmetric semi-martingale local times. I will discuss them, the definition a little bit later. Parameters epsilon, delta, and lambda are supposed to be small. So we assume that the distance between interfaces has the order epsilon. And then we send epsilon to 0, delta to 0, lambda to 0, and we would like to find the limiting process. Assume that this is like foiled material, and there are some composite material, and these foils are closer and closer and closer, but effect of one piece interface is small, of order delta. And under some ratios of epsilon, delta, and lambdas, we get a limit. Well, the most interesting case will be the case when epsilon, delta, and lambda are comparable. And we also consider, we consider two problems. At first, convergence of pair x and y, and also convergence of triple x, y, and some integral functional. Okay, the integral of the local times. And we also make these membranes sticky, and also are questioning ourselves what is the limit of this sticky process. Well, if delta is 0, for example, and sigma is 1, it is the process will be like sticky Brownian motion with stickiness at these interfaces. Few assumptions about coefficients. We always will assume that all coefficients are continuous. That horizontal coordinate is such that this parameter is uniformly positive. All coefficients are bounded. these conditions means that membranes are closer and closer, and the function d is like density of membrane. So if one membrane is located in this point, then another point is located approximately at the point this plus d times epsilon, where d is also bounded and continuous function. The local time is symmetric semi-martingale local time. It's defined by this formula or by Tanaka formula. It's well known that if x is a semi-martingale, then the local time exists. And I will not discuss today, but we can prove that if coefficients are just continuous plus condition of this positivity, then there exists a solution
Я
to
думаю, от
this
часа до полутора, вряд ли два.
to this system.
Давайте скажем час.
Maybe not
Час
not
точно.
Саша, выключи микрофон.
maybe not unique. Maybe not unique. So we don't discuss existence uniqueness for prelimit equation, but under some Lipschitz condition, we will show that the limit exists and is determined uniquely. Okay, the first theorem is the following, that the limit of our system of stochastic differential equation satisfies the following SDE if P and Q between 0 and infinity, and let me recall you that P is a limit of epsilon over delta, and Q is a limit of I'm sorry, it's a limit of delta over epsilon, and delta over epsilon, and Q is a limit of lambda over epsilon. So if epsilon, delta, and lambda, so width between membranes, effect of the local time, and coefficient between before the sum of local times are comparable. And now another question, what happens if we delay the time? So if we consider the process x epsilon delta, y epsilon delta, and composition with A inverse epsilon delta, and the answer is the following. Well, you have to make transformation of time as usual in stochastic differential equations, and when you consider composition, it converges in distribution to composition of this process and inverse of this process, and it can be shown that this composition satisfies SDE with transformed coefficient. So you have to divide here by square root of this, and this coefficient you have divided by this, and that's all. If coefficient T is okay, if one moment, so if Q is infinity, well, then this term blows up. I forgot to say that I assume that gamma is positive, and the limit process, the limit composition, is just equal to xy initial point. So this goes to infinity, inverse process converges to 0, and it's natural to expect that the limiting process does not move. Well, if parameter delta is larger than epsilon, so if the limit delta over width between membranes goes to infinity, there is no reasons to suggest that the limit of x epsilon delta and y delta epsilon exist, well, because p is infinity. However, it can be proved that if we consider some transformation of time, excuse me, here should be y, then the limit of this process and of sum of local times converge to solution of the ordinary differential equation of this form. Well, if you look at the previous page, it's quite natural, really. You see, here we have p, and p is ratio delta over epsilon, and this ratio goes to infinity. So if we make smart transformation of time, then you'll get this coefficient. Well, this term disappears, and this term disappears, and actually our solution will blow up immediately. So after transformation of time, so you speed up the time. Here the coefficient should be 0, like in the next slide. Like in the next slide. And the next question, okay, and what happens with process that slow down according to this additive functional? And the answer is the following. Our initial process, which is slowed down, just equal to this process. This process converges to solution of ordinary differential equation. So our process with similar transformation of time also converge to solution of ODE. Let me explain you that this fact is trivial. Well, assume that f and g be some function, and g is increasing, so g is this function. And let c be a positive coefficient, and let's consider this function, so transformation of time here, and fc of t is f of ct. Then the composition of c, fc, and gc inverse is equal for every t composition of f and g, of inverse of g. Indeed, inverse of this function is just inverse of c times inverse of g, and when you consider composition of this and this, you get this result. So we can talk about limit of our original process even without transformations of time. So you have convergence to an ordinary differential equation if the coefficient delta, coefficient near the local time, is greater than distance between membranes. Now, ideas of the proof.
Andrei,
Yes.
before you start to prove, let me ask you, there are a lot of works, especially we have to mention Oleinik and Hercules works about homogenization.
Yes, like Kozlov, yes, Oleinik, Zhikov probably.
And maybe Urinsky, who also did in such scheme, even he studied large variations when we have some limit process for diffusion with such periodic coefficients and so on.
Here, the problem is not in periodicity of coefficients, but in membranes, and this is different.
So Can you apply the theorem from Olenik-Zhikov-Kozlov?
I don't know how to apply this theorem because of presence of membranes.
But they also can act like some generalizing coefficient in the
Yes.
in the partial differential equations. Yes.
Yes, we have some conjugate boundary conditions, but it
Yeah.
seems to me that neither of that authors consider these.
Yeah, I understand, but the idea is that we must have convergence on some special vector. So my idea is that you can write the generator of the motion on all space, including some like generalized functions, generalized coefficients into this generator.
Yes, however, I don't assume ellipticity in this equation. And I don't know, so I assume only that this coefficient is not degenerate. And I don't know, is there existence and uniqueness of a solution for such systems?
So you just have some solution or what? Yeah?
Yes, well, I have some solution. Well, I have Lipschitz continuity in X and in Y. And I prove that any limit point is determined uniquely. And since all limits process is just one point, you have weak convergence.
Okay, let's continue. Thank you.
Well, let us consider this system. And at first, I would like to prove tightness and then to identify the limiting point. And I assume that all coefficients are bounded. So these processes are tight, obviously, and this and this and this. So the only problem is here, here, or there. And actually, I assume that coefficient beta, theta, gamma are bounded. So actually, I prove tightness if I show tightness just of sum of local times epsilon. Well, I forget to say that the most interesting case when delta, epsilon, and lambda are approximately equal. So if I show that this infinite sum is tight in the process of continuous functions, then immediately I get tightness of these. Then if I select a convergent subsequence, then it can be shown that this sequence converge to the integral of the limiting x's and y's. Probably it's easier to apply the Skorokhod representation theorem and assume that if you have convergence in distribution of x's of stochastic integrals of integrals with respect to the s or this sum, then there is one probability space and sequence of copies such that these processes converge almost surely, and then convergence of Riemann integral are just Lebesgue-dominated convergence theorem. Convergence of stochastic integrals, well, maybe with different Brownian motions, is also a sequence of very old results by Skorokhod. And the most important item is the proof that we have convergence of integrals with respect to local times to some integrals with respect to ds. So my plan is I have to analyze these sums. Then I have to prove that this sequence is weakly relatively compact, then identify, prove the theorem, and well, the last step will be simple Skorokhod representation theorem, and that's all. Okay, let us consider the functional sum of the local times. So we have these interfaces. We have a stochastic process. And let me introduce the stopping times, tau 0, tau 1, and so on. So tau 0 is the first time when you hit membrane. Tau 1 is the first time after this one when you hit another membrane. So when you hit another membrane, then you wait, you hit another membrane, tau 2, tau 3, tau 4. So it is not position. This is a position when instant of time when you hit this one. Then you hit this membrane, then another, this one. Okay, by the way, my picture is not nice. Usually you have a lot of heating of this membrane before you visit another one. And let me represent this sum of local times, of integrals of local times, as the local time that you, how to say, accumulate at the first membrane before hitting next one. Then the local time at the second membrane, the third membrane, and so on, up to a moment t. Up to a moment t. Well, and assume for a while that gamma is just 1, and I wish to get some estimate and to analyze this sum and to prove weak relative compactness. And the first question is the following. How many terms are there in this sum? What is the order? Epsilon to the -1, epsilon to the -2, and something like this. And I will show that the number of visits of different membranes up to time t has the order approximately epsilon -2. And then what is this term? This is just accumulated local time at the membrane before you visit next one. I also want to calculate, okay, and here epsilon. I want to estimate the local time, so delta local time between visits accumulated at certain membrane up to visit the next one. Well, but the local time is not nice theory, is not nice object, and in order to analyze this number of visits of different membranes or every increment, let me apply just general idea. Assume that you have some sequence of random variables adapted to certain filtration, and I would like to compare this sum with some of their conditional expectations. Well, if you consider this difference, then this is square integrable martingale. You can calculate expectation of square. You can apply Dubin inequality, and this is just application of Chebyshev inequality. And this size will be increments of taus or increments of local times. And I would like to compare them with conditional expectations. And for conditional expectations, I will get some bounds. And I will also get some bound for the second moment. And hence, I will make a conclusion that sum of increments of delta tau k, or sum of increments of local times, is close to sum of their conditional expectations. Okay, just a trivial corollary from this calculations is this. If you have sequences of certain square integrable random variables indexed by epsilon, and if you have some estimates of moments, I will have this in my calculations, then maximum of this difference converges to 0 as epsilon converges tends to zero, and the number of summands is of order epsilon to the -2. Well, so the next results are estimates, preliminary estimates of expectations of increments of local times, or expectations of moments of time before you hit the next membrane. And this is just a general result that expectation of the case moment has the order epsilon to the power 2k. I recall you that epsilon is width of membrane. Well, epsilon times a constant. And another result that this expectation cannot be small. There exists a positive constant such that conditional expectation is greater than positive constant times epsilon squared. And all of these constants depend only on upper bounds of the coefficients of our system of stochastic differential equations, and this beta also depends on the constant on infimum of this, which is supposed to be positive 2. Well, let me just give idea of the proof of this inequality. We used Lyapunov type functions and Lyapunov arguments, but at first it's easier to make some transformation of space and time. So let's make the transformation of space and time. So time epsilon squared and space epsilon to the -1. We have small interval. So it assumes that we start from 0. We start from 0 and we have membrane minus epsilon times coefficient plus epsilon times coefficient. After this transformation, membrane is, so this interval becomes A minus A plus. And after the transformation, this SD satisfies the following, this process satisfies the following SD. And you see you have epsilon small drift, delta small local time, and non-degenerate, uniformly non-degenerate coefficient near the Brownian motion. So it's more or less obvious that expectation of time for this process up to hitting this point or this point is bounded from below and from above by certain constants that depends only on upper and lower bounds of this. And similarly, the similar result is true about expectation of local time and the higher moments. And when you return back, so if you wish to calculate expectation of time for this process, then you have multiply expectation of time for this process by epsilon squared. And similar formulas for local times. So if you get estimates for this process, then estimates for this process are obtained similarly. So it is not a miracle that the result of previous lemma is true. And now some conclusions. So we have a lot of membranes. We have a path. We have moment tau 1, tau 2, tau 3, and expectations of conditional expectation. Okay, I will consider expectation of tau k plus 1 given sigma algebra f tau k. And this expectation has the order epsilon squared, and we can apply the previous lemma. This one. Let me write the following, that just T is sum over Tk less than or equal to T, delta Tk, so we have time, tau 1, tau 2, tau 3, moment T, and I sum up increments of taus. Well, and I have the last item plus something, plus the part or minus the part of the last item. So let me write here like epsilon of 1. Okay, but I know that sum of increments, well, the first reasoning. Let us consider this sum where of n times epsilon minus 2 increments. This sum has the order, so each term epsilon squared, number of terms n to the epsilon to the negative 2, so approximately equal to n, and we can take n very big number. And we have Dupe inequality, Martingale's reasoning, and this process is very close to this process. And if n is very large, then sum of these terms is greater than t plus 1. And this is close to this with high probability. So what does it mean? That if n is large, then sum of this is greater than t plus 1. So sum of this is greater than t. So hence, if n is large enough, then with high probability and with controlled probability, the number of items in this sum is less than n to the power epsilon minus 2. So the number of visits of different membranes has the order epsilon to the -2. The next step, I want to calculate sum of increments of local times times epsilon. And I know that this sum is approximately has the order epsilon to the -2, and with high probability is less than this. And again, for this process, we consider accompanying process of conditional expectations. LTK plus 1, tau k plus 1 given f tau k. And for this, we also have estimates. So this sum is close in some sense to this sum. And each summand in this sum, I forgot to write here epsilon, is approximately equal to epsilon squared. The next step, what about weak relative compactness? It's sufficient to prove weak relative compactness of this sum. And we may replace integral with respect. Okay, we can estimate this integral by its conditional expectation, because we know that they behave similarly. And then we can control modulus of continuity, and we can prove that just discrete sums of delta L tau k plus 1 is weak relative compact in the Skorokhod space, and any limit point is a continuous process. So we have weak relative compactness of such sums of conditional expectations, and hence for these sums, and hence for integrals. And hence we have weak relative compactness of our processes. So the only thing we need now, we know that this sequence is weak relative compact. We want to identify its limiting point. So now we need to find more accurate estimates for conditional expectation of local times of increment of the time before you hit the next membrane. And here is result. Well, I formulated the result if you start from 0 and membrane is located at 0, and here is sigma algebra F0, but you can prove the same if you write here increment of delta f tau cap k plus 1, and here you consider f tau k. So the proof of more accurate estimates. These O, they're random variables. They're random variables. And when I write this means that if you divide, say, O of epsilon by epsilon, okay, it depends omega, then essential supremum in omega of this is less than certain constant, and this constant depend only on bounds on coefficients of our stochastic differential equation. Okay, the proof. Again, to prove this result, we make transformation of space and time. We consider this SD, and now let us calculate expectation of x at the moment. So you start from 0, you have point A minus, A plus, and you wait until you hit this point or this point. So let's calculate this expectation. On one hand, this expectation is you hit either this point or this point, is this point time probability plus this point time probability, and we know that this is a finite time with probability 1. On the other hand, this expectation is expectation of these three terms. Expectation of stochastic integral is 0. Okay, we know, we have some a priori estimate. We know that tau has all moments. This 0. This is bounded. You have epsilon times integral of B0. This term is bounded, so it's dominated by some constant times epsilon times expectation of tau. And here you have the same. It's just this expectation is less than B infinity times delta times expectation of L taken at the time tau, and we have a priori estimate for this. So that's why we have these estimates. And so this sum is equal to O of epsilon plus O of delta, and we know that this probability is equal to 1 minus this probability. And then just algebra, and we get this estimate. By the way, this term is the answer if you don't have neither drift nor local time. If you have drift and local time, then you have to add O of epsilon and O of delta. So this is the answer for Brownian motion. And the second result, what about the local time? Okay, let's apply Tanaka formula. This plus integral of sine with respect to dx, and expectation of absolute value of x is just value. So x at this moment tau is either a minus or a plus. So value times probability, and when you consider this integral, well, you have integral of sine with respect to w, with respect to ds with delta, and times delta with respect to local time. So this expectation is equal to this. And for probability, well, we have already got the result. And after summation, we have this estimate, and the last result about expectation of tau. Okay, it is a little bit involved, but the reasoning are similar. Okay, so we have estimates. Well, we know that this converges to T. We know that accompanying sequence of conditional expectation converges to T. Then we know how to calculate the sum, the previous lemma. these accurate estimates, and we represent this as distance between membranes and divided by sigma 0, 0 plus O small plus maybe O capital of epsilon cubed plus O of epsilon squared delta. And let me recall that the number of summands here approximately, okay, has the order epsilon to the negative 2. So sum of this amount of items of this form converges to 0. So this functional converges to t. Well, and we know formulas for conditional expectations of increments of local times. And if we compare to this and our estimate, then we have convergence of this sum to t. Well, again, we apply our lemma about martingales, and the result is that this sum is close to this sum. So this sum converges to t. And okay, for example, this difference is approximately equal to d. So this density of membranes at the point A or at the point X at that instant of time times epsilon. So that's why this transforms into epsilon times d of the membrane, and times 2, because this is not consecutive membranes. It's next membrane minus previous one, and 2 is cancelled with these 2. Okay, so this functional converges to t, and well, we know that X is weakly relatively compact, and oh, excuse me, probably I have to write here some of these integrals, and so this is like Riemann sum for this integral, and we know that this Riemann sum converges to t, so the integral also converges to t. And next, this integral is just sum of the local times. Okay, here notation is not so nice. I have to write here sum over all k, so this. Well, so we have convergence of something to t, sum of certain integrals. And what is the difference between this and this? We multiply by gamma and we divide by this integral. So these sums converge to integral with respect to t of gamma times inverse of this. And I forget to say that, well, we apply Skorokhod representation and work on one probability space. And for some copies of our processes, we have almost sure convergence. And here convergence to t means that these processes converge locally uniformly to t. And here also we have locally uniform convergence. And then we return back to our SD. This converges to integral over ds of a certain functional of any limit point. And similarly, these thumbs also converge to certain integral functionals, and then it can be easily seen that these converge to stochastic integral, these converge to Riemann integral, and these converge again to Riemann integral as it is written in the theorem. So that's all. Thank you for the attention.
Okay, thank you very much. And maybe somebody have questions or comments, please. Still, Andrei, can you write generator of the pre-limiting question process and limiting process? Yeah?
Yes, I can.
Mhm.
Well,
And
theoretically, I can, but yes. Mhm.
you see, still, it looks like you have some statement about the convergence of such generalized partial differential equations or related semigroups. Yeah.
Yes, but prelimit. You see, these preliminary processes, the generators have some boundary conditions at these interfaces, and the limiting process does not.
Can we transform these boundary conditions into generalized coefficients in this generator? You see, this is my point. Just to consider such generator where in differential operator we have some generalized function.
Yes, actually, yes. These membranes are like, so let me show you. So informally, this is delta times beta, probably divided by that coefficient sigma 0, 0 times delta delta function. Okay, this is delta function at the point a k of x of t dt. So informally, this is generalized drift with this is generalized drift with delta functions. And well, in some sense, some of delta functions converge to a function that we get in a limit. This is true.
So maybe you can have some purely analytical proof, yeah?
Maybe yes, but it may be complicated because you have, okay, analytical solution was constructed in works of Mykola Ivanovich.
Yes, I remember.
So you have to analyze these perturbations of the density, say, of the process without these membranes. And this is not trivial. This is not trivial. And I would like also to stress, we don't assume that these coefficients are non-degenerate.
Yes, you already said.
This is the first. And then we can also have very degenerate drift. For example, assume that this is 0 and this component is not 0. So you behave like a diffusion. When you hit membrane, you have a slide, and this is some special case of perturbation, which is also okay, but yes, it's possible.
Okay, let me ask you the following question. Considering your limiting process, where you have like infinitely many very closely placed but very small membranes,
Yes.
then can you say something about the how its diffusion coefficient change in order that we can say, for example, if we start from Wiener process without any problems with those sigma, then we know that it goes to infinity like law of iterated logarithm. We can write it, yeah. But now, how this small delays related to local times change the
You mean
speed of
this? You
growth?
mean
Yes,
this term?
yes, yeah.
Yes. So
Mhm,
it's just classical result
mhm,
that you have this, and
mhm, mhm.
you have to divide drift by
Yes,
square root.
I know how to get it, but
Yes.
my question is how the membrane cause do they cause delay or not? Do they cause decreasing of the speed of
Yes, decreasing. Yes.
yeah. Mhm,
If this
mhm,
is greater than 1,
mhm,
so the speed decreases. Yes.
mhm. Okay. So you can predict the such properties like law of iterated logarithm or Levy model continuity for limiting process from the properties of your membrane. Yeah.
Yes. Actually, there is interesting question. Okay, if delta is greater than epsilon,
Mhm.
then generally this term converts to plus infinity if beta is large.
Mhm. Mhm.
But there may be a possibility that assumes that membranes are periodic,
Mhm.
and one
Mhm.
membrane, for example, pushes a little bit right, next left,
Mhm.
next right, next left, and so on and so forth, where delta is, say, square root of epsilon, probably.
Mhm. Mhm.
And then in a limit, they theoretically they may compensate each other.
Mhm.
And you might, so I don't know the answer, but theoretically it's possible that delta is bigger than epsilon, but membranes are like, I don't know, dipoles. So one is
Mhm.
here, one is there, or other sides. And in a limit, this may produce something new. Maybe some perturbation of diffusion coefficient, unusual.
Mhm. Mhm. Okay. Mhm. Okay, thank you very much. And if there are no other
I
questions,
wanted to ask, so
mhm.
what was the most difficult or interesting part of the proof?
Uh, uh, okay, so it was well. Now we see that the proof is not so difficult after say 1 year of calculations. We discover that if you replace if you compare, so there are a few steps. Compare sums and conditional expectations, then obtain some preliminary estimates for expectations. So this was quite standard, and uh, we were amused that some exact estimates can be obtained even without high regularity of coefficients and we just use some properties of martingales and so on and so forth. And it's also it was not obvious that if delta is much larger than epsilon, well, delta is a coefficient near the local time. Delta goes to 0, epsilon goes to 0, and if delta is greater than epsilon, then after some scaling of time, we get just an ordinary differential equation. And if we consider these processes with delay, then we obtain the same ordinary differential equation. Well, we didn't understood at the very beginning that here should be 0 in both cases. Well, but this is true, and this result was not clear.
Thank you.
Okay. So thank you very much. And maybe Georgi know who will be the next speaker.
Next speaker will be Gennady Navrotsky
Okay.
about winding numbers for Gaussian processes on the plane.
Very good. Okay, then for today we finish our work. Thanks everybody, and bye up to the next week.
Thanks, bye.
Goodbye.
Bye.
Goodbye.